The first topic is going to be the equations related to E field. So we first know that E field equals to KQ over R square, and sometimes we put KE here to represent the constant, and then E field is a vector, and this R is a vector going from your source, no matter it's a positive charge or a negative charge, going from your source to your observation point, the unit vector of that direction. If you have a positive charge, the E field is in the same direction as that. If you have a negative charge, however, the E field is going to flip direction and pointing toward the negative charge instead of pointing outward, away from the source, away from the charge. And this is also equal to 1 over 4 pi epsilon 0 Q over R square R cap. Okay? And this KE is a constant, which is exactly this part. They are identical. And here something very important is that this equation is for a point charge. It's not for a charge with a particular size and a shape, like this shape or a ring or a bigger size. Okay? It's only true for a point charge. And the R here is the distance. It's not a radius of your spherical charge whatsoever. It's the distance from your point of source to wherever you are trying to figure out the E field. R is the distance, and this R only represents the direction. And that is a unit vector which has no length, or you can say it has a unit length equal to 1, and it only points to the direction. Okay? This is the equation which is very useful to calculate the E field due to one point charge. Okay? So what happens if you have more than one charge? So if you have n discrete charges, which are points, okay? If you have n points which are not connected, then what's going to be is that you can figure out each individual E field created by your charge I. So if you have n charges, I goes from 1 to n. For each of them, it's creating an E field like that. Okay? So imagine that if you have a charge here, a charge here, this is a positive, and this is a negative. If you have two of them, what kind of E field you're going to get at this location? Okay, so this charge is positive. It is going to create an E field. This is your Q1. This is your Q2. Charge 1 is going to create an E field, E1, in this direction. Because it's positive, the E field is going away from it. Charge 2 is negative. And this charge is going to create an E field pointing toward the negative charge. So your second charge, due to charge 2, it's also going to be in the negative, in the same direction, pointing toward charge 2. This is your E2. Okay? E1 is in this direction. E2 is in the same direction. What's going to be your total E? Your total E field is equal to your E1 plus E2 due to these two charges. However, it is dangerous to add them together. Keep in mind, the E field, they are vectors. When they are in the same directions, the two values add directly. However, in some other situation, these two values can be in opposite direction. So when you add two vectors, you have to consider their directions and cannot add them directly. For example, what happens if you are located here? If you are right here, the first charge is going to give you an E field pushing away from the positive charge. And because you are very far, this field is not very big. It's a small amount of E field coming from your first charge. What happens to your second charge? At this location, however, your negative charge is going to provide you an E field pointing the negative charge pointing away from your location P, and it's pointing toward negative charge, and that's your E2. In this case, you have E1 in the x direction, E2 in the negative x direction. When you add these two, you are not adding those two numbers directly. You have to consider the difference between them. Okay, so now if we have n charges, it's easy. Each single one of them, we consider each individual charge. We consider different distance. Here is the distance from the I to P. P is the location where you observe that particular point. I, it's the particular Q1, Q2, Q3, whichever you are. So this is your R1. And the other one, the distance from here to here, is your R2. Okay, R1 to P or R2 to P. Okay, so using different Q, different R square, and a different vector pointing from the charge to the location, you figure out the different vectors of each individual E field, and then you add them. If you have two, you add them two. If you have more than one, you are doing the sum of the E field for each one of them, and your I goes from 1 to n. That gives you the E total. And that's a vector, okay? Keep in mind. Especially if they are not along the same line. If one is in one direction, the other is at an angle. If this is your E1 and this is your E2, you have to add them as vectors. You have to consider the x component, y component, and adding them. Okay? So it's not going to be simply this particular value plus that value. So next, this is when you have n discrete charge. What happens if you have a continuous charge? Continuous charge means instead of individual points, you have a long rod, or you have a sphere, or you have whatever shape. It's not very small, it's not a point, it has a particular shape. When you have that, what happens? The idea is that you can always take a small chunk of that, cut a tiny piece out. Imaginally, not really cutting out. Imagine that you are cutting a small amount of dq. That's not a total amount of q, but a small amount of dq. And consider this small amount of object. You can consider that to be a point charge. And then, if you are going to figure out the E field created at this location, what you do is that you know each of this dq gives a small amount of dE. For example, if the charges are positive, this small amount of dq is going to provide a small amount of E field pointing away from the charge at this location. That's the contribution from this. To be consistent, this is a red-pink color. I'm going to use the pink color to represent the small dE created by that. Okay? This is from one of that. If you consider another piece, maybe here, another small amount of dq, and that's going to create another small amount of dE. Because it is further away, it creates a small contribution. Whatsoever, what we can do for continuous charges, we can cut the entire object into tiny, tiny pieces, infinite number of small point charges. And each small point charges gives you dE. And apply the same equation here. For each small charge, it gives you the small amount of dE, which is equal to Ke multiply not the total amount of Q, but a small amount of dQ over the distance R. And the distance is not the center to center distance, it's not a short distance, it's the particular distance, the pink one. This part is going to be corresponding to this r. That's the particular distance you apply for this object. And for this object, you have a longer distance. That distance square. And then the r is a unit vector going from the source to that point this way, okay? This is true for each individual dq. That's not the end of the story here. When we have 2, we add 2. When we have 5, we add 5. Here, we have an infinite number of small amount of dq. The total E that we need is equal to an integral of all the small contribution, which is equal to all this, okay? However, you don't integrate vectors directly. What does that mean? You remember one of our famous homework example where we have a circle, a charged ring, and this ring is going to create an E field for you at a distance x away from the center along the axis, okay? You have a perfect ring, and then you take a small amount of dq. That's going to create an E field pointing along this direction here. And then you have another small amount of dq that's going to create you something along this direction. You have an opposite one here facing the first charge, and this dq and another dq. That's going to give you this. So all these adding together, they gave you many of small de. None of them are in the same direction. You cannot integrate them together. That's a big no-no. Stop right here. So what can you do? What can you do is that in this case, when you have a small de, you can consider it is x component, dex equals to de multiply cosine this angle. And then you can figure out your ex equal to integration of daex. Only after you decompose your vector into the x component, you can now do your integration. Similarly, what happens in the other direction here, you have for the dey or de perpendicular. The total E field in the y direction equals to the y direction integral. And in this particular case, we know when you have one charge here, it gives you something downward and to your right. And the opposite to that, you have something upward to your right. And because of the symmetry, you know the downward part and the upward part, perpendicular part, they cancel each other out. In this particular case, you know the other components, they all cancel out, up and down, front, back, and only the remaining part is in the x direction. In other cases, this may not be true. However, keep in mind, you cannot do your integration while you are dealing with a vector because those values, they don't add together. They are all in different directions, and then we will have to decompose them into different directions. As long as they are all in the x direction, you can integrate that. As long as they are all in the y direction, you can integrate that. So that's how we figure out E field using a point charge equation. Do not apply this equation to all the situations. It only applies to point charge, and we can do that for endpoints. We can also do that for continuous cases by cutting everything into small pieces of dq. A related topic is about Gauss' law, and we are going to talk in a different time, in a different topic, tell you what Gauss' law is, and then in what situation we are going to use this dq method to calculate the E field, and in what situation we are going to use the other method, which is Gauss' law.